For a long time now, we've thought of the brain as this incredibly complex map of connections. But what if that's only half the picture? Today, we're diving into a new model that looks beyond the roads and starts paying attention to the traffic.
This quote from the research just hits the nail on the head. Network neuroscience maps the roads. BKM explains the traffic. That one sentence really changes everything. So, to get it, let's start by understanding the roads before we get to the really exciting part, the traffic itself.
All right, Section 1, the brain static map. To really appreciate where we're going, we first have to understand where we've been. Let's look at that beautiful but ultimately static road atlas of the brain that neuroscientists have been building for decades.
So for ages, the main way we've looked at the brain is as a giant network. You've got these regions, which we call nodes, and then all the connections between them, which we call edges. And this has given us an incredible map for sure. It tells us exactly who is connected to whom. But here's the thing. It's like a perfect road atlas with no cars, no movement, no life. It's the structure, but where's the action?
And that brings us to the really cool part. Section 2, meet the brain's traffic. The big idea here is that thought isn't just about which parts of the brain light up. It's about how energy and information actually move. And this is the core of a new theory called the Brain Kinematics Model, or BKM for short.
The absolute heart of BKM is this concept they call strain flow. So instead of just seeing brain activity as different regions blinking on and off, I want you to imagine a directed current of energy and information. This flow, that's the actual traffic moving along the brain's highways.
And get this, BKM proposes that every single cognitive event has a life cycle. It follows this really predictable path. You have an onset, where an idea or a piece of information kicks things off, then it builds to a climax, where it's all fully integrated. And finally, it has a discharge, where it turns into an action, or maybe just the next thought. It's a beginning, a middle, and an end for every single thing our mind does.
Okay, so if thought is traffic, there have to be some rules of the road, right? Well, that brings us to Section 3, highways and zip states. This is where we're going to look at how this entire flow gets organized.
So if you zoom way out and look at the big picture, the brain's traffic tends to organize itself into this really elegant butterfly shape. The wings are your left and right cortices. The body, or the medial spine, is the cingulum bundle, and it's what keeps everything coherent. And so important, the corpus callosum acts as the coupling that links the two sides together. This isn't some fixed loop, it's a totally dynamic structure that changes all the time. So we've got this amazing, large-scale structure, but how does it change? How does our brain shift gears from, say, intense focused work to just daydreaming? Well, the answer lies in this absolutely crucial concept called zip states. And these zip states basically come in two flavors. First, you've got zip-in. This is a compression of the flow. Imagine all the traffic merging onto a single superhighway. It's narrow, it's focused, and it's moving fast towards its destination. Then you have zip-out, which is the total opposite. It's an expansion. The traffic spreads out onto all the little side streets, exploring tons of different paths at once, which, delays the final arrival. Okay, this is where it all starts to get really, really fascinating. Let's take these concepts and apply them to something we all experience every day, the huge difference between being awake and dreaming.
And just look at how the data maps onto this BKM model. When we're awake, our brain shows all the classic signs of a zip-in state. The butterfly wings are narrow, the connection between the two sides is tight, and we have strong discharge into action. But then, in dreaming, it completely flips. It becomes a classic zip-out state. The wings get wide, the coupling loosens up, and that discharge is suppressed.
So let's just lock this in. Your focused waking brain, that's the brain zipping in. It's compressing thought into a stable, super efficient pathway that's ready for action.
And dreaming is the polar opposite. It's the brain zipping out. It's expanding into this high-dimensional, exploratory state where all these different ideas and memories can just recombine freely.
Now, this model doesn't just explain normal brain states, it also offers a really powerful new way to understand what happens when the traffic breaks down, giving us a whole new framework for thinking about mental health.
So instead of seeing disorders as just a chemical imbalance or a wiring problem, BKM lets us see them as failures in the flow control system. It's like the brain gets stuck in one particular mode of traffic.
This gives us a whole new language to describe these conditions. From this point of view, ADHD could be seen as a system that's locked open, right? It just can't maintain that tight, focused zip-in. Depression might be a locked-closed state, stuck in these rigid, ruminating loops that never quite discharge. And psychosis? That could be like a broken zipper, where different streams of thought just fail to bind together into a coherent whole. It's a huge shift from a purely chemical view to one that's much more mechanical or kinematic.
So, what does this new model of brain traffic ultimately give us? What's the big takeaway here?
At the end of the day, the Brain Kinematics Model isn't just another theory, it's a whole new way of seeing. It gives us a unified framework for everything from waking focus to dreaming to mental health. It reframes the role of brain waves and points toward new diagnostic tools. I mean, imagine brain scans that don't just look for activity, but for the actual geometry of that activity's flow. And maybe most importantly, it builds a real bridge between our subjective internal experience and the objective things we can measure in neuroscience.
And that leaves us with one last provocative thought. If our thoughts, our dreams, and our moods are all just different patterns of traffic flowing through our brains, could we learn to become better drivers?